Is your permission? Hello. So today we have a final presentation of projects after Lviv Data Science Summer School 2025, and we have 7 projects applied for a contest. And of course, it's not only about the prize and contest. It's basically about synergy and work with um, mentors and with data. So I hope you enjoyed these projects, and I hope that we can create something great from this later. But for now, for now we have 7 projects presentations. So we have 10 minutes for presentation and up to 5 minutes for questions. And I encourage you to ask questions. So uh, it would be more or less like this. Um, and we have preliminary grading for application for projects. And after your presentation, we will. I think that mentors and organizers, we will make a closed meeting with everyone in waiting room, and we negotiate and agree who is the winner, and then we announce the winner at the end and close the school. So if you have any remarks or questions, then if no, then let's
Sounds good, yeah.
yeah, thank you. So let's proceed to the first project. It's a winter wheat yield prediction with technology data by Yegor Yanvaryov. And Yegor, I give you, wait, give me a second. I will give you permission to, yeah, you can
Yeah.
now share your screen, I think.
Yes, thank you. Good evening. Today I want to present you a machine learning system I built for winter wheat yield prediction. Yield prediction is a critical challenge in agriculture, especially for winter wheat. Accurate forecasts are essential for agribusiness planning, logistics, and trading. I developed a baseline model using weather and NDVI indexes, then extend it with operational data to compare performance improvements. I also construct confidence intervals for predictions. The target is winter wheat yield in tons per hectare. Features include weather metrics, weekly NDVI indexes, field coordinates, and field operations data. I train models weekly from 2 months before harvest up to the harvest date, compare performance with and without operational data, identify important features via SHAP, and construct confidence intervals. This model supports agribusiness with enhanced decisions, logistics with better planning, better resource allocation, and trading with production forecasts. I work with 2 data sets. The primary data set, the DF main, contains weekly weather features and NDVI indexes. The second data set, the DF operations, contains detailed field activities like fertilizer operation applications and works. Together, they encompass 783 agricultural fields in Ukraine. I create a categorical feature region cluster based on geographic coordinates to stabilize data splits across faults. To do this, I transform the coordinates from VGS 84 to UTM and then apply hierarchical clustering with 4 clusters using word linkage in agglomerative clustering. I clean DF main by filtering missing culture values, remove previous year columns, and exclude features for weeks after harvest date. I obtained features for 25 weeks, 281 total, then remove 6 low significance weak features based on SHAP, reducing it to 131 features. I process the DF operations by renaming columns and manage operations with 30-day gaps. then create a per field operation history for integration into the extended model. After preprocessing diff operations, I experimented with different approaches to convert textual operation data into numerical features, starting with basic methods, progressing to advanced embedding-based techniques. I started with a bag of words on my own preprocessing of the Ukrainian language, and also tried TF-IDF with specialized tokenization. However, these methods produced high dimensional features that had no semantic meaning and did not rank high in SHAP scores. So I explored more advanced techniques. I generated embeddings using two multilingual models, sentence transformers and Alibaba NLP. I applied PCA to preserve 95% variance, then tried k-means and dbScan for clustering. Neither improved performance, so I applied more advanced techniques. To improve clustering, I optimized UMAP and HDBScan using Coptuna to maximize density-based clustering validation score, tuning parameters across 300 trials. I visualized the clustering results in two-dimensional UMAP and TSNE plots. The sentence transformers model produced more coherent clusters than Alibaba, so I selected it and saved the results in HDBScan operation cluster, combining it with features from DFMA. Now pipeline training. I implemented LightGBM pipeline for mean estimates and quintile regression, 5% and 95% bounds, to form a 90% confidence interval. Models train weekly from 2 months before harvest onward, progressively excluding future features to assess accuracy over time. The pipeline includes cross-validation, holdout validation, visualizations, and sharp explanations. I configured LightGBM models with following hyperparameters. For the mean model, I used regression as an objective. For quantiles, I used quantile regression with alpha 0.05 for the lower bound and alpha 0.95 for the upper bound. I used 5-fold stratified cross-validation by region cluster feature to ensure the stability of the metrics. For each fold, I trained 3 models, mean, lower, and upper, with early stopping after 25 rounds, based on mean absolute percentage error for mean and pinball loss for quantiles. I averaged metrics across folds and retained models on full training data. I assessed accuracy over weeks 20, 28, dropping future features per week, and trained models using cross-validation and visualized how accuracy improves closer to harvest. Evaluation metrics. Mean absolute error measures average prediction error magnitude in the target units. Mean absolute percentage error express error as a percentage of actual values, useful for comparison, but sensitive to near zero values. R squared includes how well the model explains variance, closer to 1 is better. And pinball loss, also known as quantile loss, is used to quantile regression to evaluate predictions at specific quantiles. If the alpha value is less than 0.5, then overestimation is much more expensive. So the model tries to underestimate the target. If the alpha is greater than 0.5, underestimating becomes more costly. So the model tends to overestimate the target. I saved a training configuration JSON with random seed, embedding model name, feature list, and prediction weeks range for reproducibility. On the validation set, I filtered features similarly to train for each week. I made predictions with the final models and computed validation metrics. I computed the shape values for each model type, mean, lower, and upper per week, using tree explainer on the validation set to identify important features and their contribution to predictions. We can see shape values and confidence intervals for each week. In the forecasting tab, users upload new data in Parquet format with weather NDVI and operations features. The data is preprocessing through the pipeline, data preparation, embeddings, generation, and clustering. I make predictions using the trained models for a selected week. We can select samples. I just select 5 random field IDs to show how it works. One second. And operation sample. Here, users can filter predictions by week and field ID and view results, including predicted values to confidence intervals. Here we can select field ID number 7 and look at the predictions, lower bound, upper bound, mean prediction, and compare it to the actual value. Conclusion: this system achieves from 9 to 12% mean absolute percentage error with calibrated confidence intervals and good interpretability. The Stream Elite app is accessible for non-technical users. All code is open source on GitHub with saved models and fixed random seeds. The pipeline is modular, retrained on new field data with minimal changes. The system is ready for deployment in Ukrainian agriculture. Thank you. Happy to answer your questions.
Thank you. Thank you for a nice presentation, especially very nice graphics. If anyone have questions, please. Yeah, please, Raul.
Yeah, I wanted to ask you about the main driver of the wheat yield. Since you did the PCA decomposition, did you figure out what was the main driver of the yield? What is the influence of the weather, soil composition, humidity, hail? Can you comment on that?
Thank you for your question. I tried to use PCA, but in final pipeline, I didn't use it. I use UMAP plus HDB scan for pre-process operational data. And this the second question, yes, I analyze the shape values for each week, and as we can see, for example, NDVI mean is the most important feature for each week. For example, for week 26, NDVI feature not so important.
Remind me, what is NDVI?
It's a satellite index from the analyzing image of the field from satellite.
But what does it mean in What does it mean in physical parameter? Is that the humidity, the rain, the soil, the nutrients? What is it?
It's like how much is green your field on the picture.
Okay, but do you have any information about what is driving the greenery of the field? I mean, why is it greener or not? I mean, do you know how it correlates? Because, for example, it would be interesting to correlate your results with humidity, temperature, soil reflectivity at that time to understand what the farmers did well or wrong.
It's highly correlated with all temperature parameters like, as you said, humidity and temperature. Here we have evapotranspiration. It's like humidity of the field. It's this NDVI mean includes a lot of weather features, and it's highly correlated with these weather features.
Okay.
I believe it's some kind of data leakage, maybe, because it's like satellite says your field is very green, so you have a lot of crop. So your crop is
it's
good.
like correlation high, yes.
So maybe
I think it would be nice to pin down which one is the one that the farmers need to use, right? Is it better nutrients, or they just need to wait for good weather? I mean, is it can they do anything to build better yields, or is just good weather? For example, it would be interesting to check here what you have here, right, in this area, right? You know, here, right? Which one is the one that has most signal, right? Either you can do PCA or the autoencoder if you want to do nonlinearity dimensionality reduction and see which one is the one driving the farmer. I mean, I'm just curious because it looks like you did 95% of the work. Like maybe you can do the next 5% and you will get a very interesting result.
Yes,
it can well improve.
I want to say it's because we have some limitations. We have only 781 field, and I can't build like autoencoder or something because it's not enough data for a lot of columns. I have 281 columns before cleaning, and I based on the chef values, I remove 6 columns. For each week, it's like 150 columns.
Okay, let's.
Yes, we need more data
let's
to
go.
do deeper research. That's why I do like this. Thank you.
Maybe last question. Did kernel approve this idea? Did you talking to them? I mean, is it in process of implementation?
Yes, I also built this this tab with forecasting and send it to them. And the project on GitHub have all steps to implement this. And they checked on their 2024 fields data, and we get these metrics. It's a little bit worse, but they checked my model on the new data, new unseen data. Like on week 28, we have 15% mean absolute percentage error, and they can analyze on these plots on the shape values what was important or what feature wasn't important.
We should ask their feedback also. Maybe it's for us or for the school. It would be really interesting. Okay, thank you. Any other comments, remarks? No. Thank you. Thank you and now we'll go to next presentation. Bit processing machine overload prevention. Mikhalina Bondarenko and Victoria Patnaya. So please, can you
see my screen?
Not yet. I mean, there's some delay.
Okay, it tells me that I'm screen sharing right now. Okay, I may try again. Okay, so do you see it now?
No, we see some kind of mix. Maybe can you share not whole screen but only window with presentation or something like this?
Okay, I
Yeah,
will try.
now it's good. Yeah, now it's good. So you just
Oh,
mix screens. I think yeah. Now we can see. Please
okay,
start.
so okay, thank you. Thanks a lot. So I will start the presentation of these sugar beet overload productions. First of all, let me put you into the context because you might have forgot our tasks. So at the sugar beet plants, we process beets into sugar, and during the season which these beets are harvested, they are processed into sugar 24/7 without any stops, preferably because stops they eat up money, they cost money because it's a lot of money, and the produce may actually go bad. But unfortunately, these stops are inevitable since the fatigue and lack of experience of some of the engineers can cause machine overloads, which cause breakdowns, which cause the stops of the machine and very complicated processes to repair it. So also the other problem is that training operators is really difficult because once you put in some changes to the controls, once you influence the system, you actually see the results of your actions in a time distance of an hour or more from your actual inputs, right? So you don't see the results immediately, which complicates the training process of operators. So we tried to help this problem with machine learning. Okay, so first of all, the contents of this presentation. The first thing I will show you is the data that we used, which data we have collected, the data sets that we have collected, which data processing, the challenges. The next we'll talk about the overall prediction, which is the first kind of solution to the problem that we have, and the secondly we will talk about machine dynamics modeling, which is a second approach to the solution of our problem to help the operators avoid overloading of the machine. Okay, so first let's talk about the data. But here you can see an illustration of the interface we used to extract this data. Why did we need to extract the data at all, you might ask? Well, the problem is that the old data set that we were provided with was really small. It had 1 minute discretization. It had no control signals, which meant the old data set did not have the what the operators were doing inside of it, right? It only had some select 13 columns, which was not enough for accurate prediction. So we decided to collect a new data set that has 84 non-tangent columns. It has many various, it has also the control signals, right? So it also has what the operators were doing to the machine, which will be really beneficial, as I will show. And it had 1 second discretization, which allowed us to try to tinker with it and see which discretization is best. Yeah. Now let's talk about the control signals a little bit. So when we examined the control signals, we noticed that sometimes they were constant and sometimes they started fluctuating. And the reason behind this was that actually the control signals, the operator, right, of the machine could set the control signals themselves, but also they could delegate this to the microcontroller at the plants. So the microcontroller sets the control signals for them. And to help the model understand this, we added a new column that signifies which periods of the data this exact control signal is automatic, is controlled by a microcontroller, and which periods it's set by the operator. There were also, like, in the data that we collected, it was real data. As we can see, the sugar beet processing machine, it stopped for some periods. So and it also was not operating at full capacity at some periods. So we had to eliminate this. And since only the high current periods were susceptible to overload, we decided to keep them and to remove the periods where we had no data, for example, and we were left with only this more than 170 amperes data, which we use for training. So how do we help prevent overloads? So in this context, we think about how would we help the operator do the correct thing to prevent the overload. So one solution is that we can show them a % probability estimation of the machine overloading in the near future, for example, in the next hour. So right now, there is, for example, there is a probability of 70% that the machine will overload in the next hour. So you should probably do something. You don't know what's right. You can know what's right, as we will show later, but you don't know, right? You see this percentage for it, and you see that, well, I'm at high risk right now, I should do something, and you do something right now. And you see how your actions affect this percentage point. The second way we can help the operators is that we can actually predict the whole machine dynamics. So we can show them, well, if at the current state of the machine, in the next hour, this value will be increasing with this dynamics. Right, so we will show them a graph, right, of how it will increase. And when they do input control signals, they will see that these predictions might change, and so this will help them prevent overloads. Okay, so let's look at how it is done. First of all, the overload prediction, the simpler part. Actually, what you will find really interesting is that vanilla logistic regression was the winner of all the models that we tried, and other models performed worse. And why would that be the case? Because even though the data we decreased the data discretization to artificially increase the amount of data, we increased the number of columns, the models could still memorize the data, the by-second data, as well as the by-minute data, because the variations were not that high, actually. So when we, the data, like the dynamics were quite slow. So even if you train the model on by-second data, right, on the second discretization data, it could still memorize the whole data set, as well as the model that would be trained on by-minute data, right? But also, when we discretize by minutes, only 24,000 rows are left, which means, and even more, even furthermore from that, each row in the data is every minute, right? So it's the prediction is for the next hour. So the prediction for every 60 rows actually overlap, which allows us to overfit the data really efficiently, right? Yeah, so the reason that the vanilla logistic regression works best here is that it overfitted the least on the data. Now we go to the outcome modeling. So the idea is that we can predict machine dynamics of each column of the data set autoregressively. To the operator, we will show the how the dynamics will change over time, and they will see how their actions affect the dynamics. As an additional benefit, of course, this gives us more data to work with, as now we don't have just one target. We have a whole hour of 85 possible values to predict. Okay, so now for the approach. As the first thing we tried was the autoregressive transformer with teacher forcing, which means that we predict basically the next minute, the 85 values for the next minute. And then when we predict the minutes after that, we put real values, the actual values that happens at the input of the transformer, which means that it only learns to basically to predict the next minutes, right? So it does not learn to predict the whole 60 minutes in one go. It only learns to predict the next minute. And the problem with this is that when we run it to autoregressively predict a whole hour, the errors compound, and we see that the predicted dynamics of our current, they diverge massively from the data, and we have a huge loss, right? And we observe a huge loss. So how do we mitigate this? Let's disable teacher forcing and predict the whole hour during training. So we for given like 1 hour as an input, we predict the next hour autoregressively, and at each step, the outputs of the model are placed in the inputs, and the loss is formed by assessing the whole predicted hour, not just not just every minute, right? This allows us to improve the test loss actually, but when we look at the prediction, we see that actually the machine dynamics were not predicted, and the model.
It's time 10 minutes already.
Oh, I will speed up. Okay, thank you. Okay, so this doesn't allow us to predict model dynamics. So we add a teaching forcing scheduler, which basically we start at full teacher forcing and go to no teacher forcing. This improves the results a little bit. Then what we do is we fix the control inputs. Since we don't want to predict the operator behavior that is embedded in the dataset, we only want to predict the machine behavior. So we fix the control inputs and we see even better results. Now, there were limitations to this. The things, the dataset that we have collected does not actually have a couple of control inputs, so we still predict the operator that was using the machine during the data period that we collected. And the data only encompasses a single month, which is a problem. We should collect more months. And we should be able to evaluate actions based on predicted model dynamics. So an action recommendation model can be constructed and should be constructed. And also we want to work on a human-machine interaction with our model. As a bonus, here is a sketch of the interface design, which we used linear regression for, linear logistic regression for. And thank you to the questions.
Okay. Thank you. Any questions about this project? Yeah, please, Rod.
Yeah, sorry. Yes, like so. I'm curious that this must be some kind of catastrophe theory Poissonian process where the thing fails because either the machine is too old, the workers are overstressed, they forgot to oil the machinery. Isn't it better to use some kind of a stochastic Poissonian process to model this system?
So can you explain your question a bit more, because I'm not sure I understand you?
Okay, you are trying to figure out how and when the system is failing, right?
Yeah.
Now, these failures are not systematic failures unless you focus on wearing and tearing of the machinery. But they're usually failures because of random events happen at the same time. Basically, a worker was tired, or the night before, he or she was fighting with their partner, they're upset, they come to work, and then they forget to oil the machine, right? And then the whole thing fails, right? So there is very little correlation with past data. It's much more of a Poissonian random stochastics event, in the sense that you are having some kind of attraction points, if you want to talk in the catastrophe theory language.
So this is. Mm-hmm. Okay.
Go ahead.
Okay, so this is why we wanted to isolate the control inputs from the other columns, right? Because we want to isolate every external value that affects the machine, and only predict the machine dynamics given these external influences, right? So these external influences can include the quality of the produce that we input into the generator, and all of the controls that the operator can affect. We suppose that the machine does not wear down. So the aim was to predict the machine dynamics, right? It was really hard to predict the machine dynamics using like a physical model, because you would have to model a lot of things and no computer can compute this. So we use machine learning. And when we are able to predict machine dynamics, given the control inputs, this actually gives us the benefit of seeing how our control inputs affect the machine and how they would affect the machine in the future, right? And so the predictions, they actually, so this is actually the problem that we try to tackle, is that the data set contains these random events and we don't want to learn them, right? So we isolate them. So we isolate them by always providing them and the inputs. So when for this last thing, right, we have provided the control inputs for the whole hour, right? So we only predict the machine dynamics, but the hour's control inputs are given, right? So this is does this answer your questions?
Okay, I don't want to take more time because we are short on time, but thank you for the answer.
Thank you for the question.
Yeah, thank you. I also have very short question. Why these nice plots are not in your report? I mean, it's something last.
Well.
Okay. I understand everything. No need to explain. But yeah, it's good. Okay, thank you. Thank you for your presentation. And the next presentation is Andriy Mavrin, Sofia Manько, Lisa Kaminska, Ianya, Anna Vechirska, and Andrei Rikovka, Yield Map Restoration. Who will be presenting?
Sofia Manько.
Sophia, are you here? I definitely saw her, but right now I don't see her anymore. Maybe something happened in her. Oh yeah,
Isn't there Sophia there? I thought very much.
Now she's
Okay.
here.
I'm sorry. I will be presenting. Okay, you can see my screen now.
Yeah.
Yeah, but go to presentation mode or something. Yeah, so we can see all image. I mean, right now
okay.
we have a lot of extra stuff. Yeah, thank you.
Good evening. My name is Sophia, and today I will talk about our project Yield Map Restoration. Modern farm machine can measure yield during harvest and save each value with GPS coordinates. But the sensors aren't flawless. GPS breaks, bad calibration, or small hardware errors often create missing spots on the yield map. Our goal is to fill those missing gaps. Using satellite images from the whole season plus a digital elevation model, we train machine learning models and neural nets to predict the yield in places where the harvesters didn't record anything. In this project, we built a unified geospatial dataset by combining yield maps, Sentinel-2 imagery, and trained features for 25 fields. All yield rasters were projected to universal transverse marcator and resampled onto a common spatial grid, since the fields originally had different resolutions and varying levels of completeness. For each field and period of dates, we doubled Sentinel-2 bands together with a scene classification layer to filter out clouds, shadows, and invalid pixels. Using the spectral bands, we generated vegetations and moisture indices such as NDVI, GNDVI, NDRE, SAVI, EVI, and NDMI.
Teresa? Sì, dimmi Teresa.
Sorry?
It's fine. It's just Raul didn't mute himself. So continue.
Okay. To capture crop condition more robustly than raw reflectance. We also incorporated dam-based terrain features, slope in X and Y directions, and RMC slope, because microrelief influences water distribution and yield patterns. As a result, we obtained a harmonized multi-layer raster stack for every field, with all features aligned on the same grid and ready for downstream models. First of all, we tried a machine learning approach. And in this part of the project, the first challenge was that every field had a different number of satellite images. To make the dataset consistent, we split the whole growing season into 10 time intervals of about 13 days. In each interval, every field must have at least one image, so we always work with the same number of time steps. If a field had several images in the same interval, we simply chose the cleanest one, the one with the least clouds based on the mask. And if two images were equally clean, we took the one with the strongest NDVI contrast. For the modeling, we used XGBoost in a pixel-wise setup. Each pixel is treated as an independent data point with spectral indices from multiple dates, trained features from the DEM, and Gaussian blurred masks as a bit of spatial context. We normalize the data and trained XGBoost with a standard train validation split. In our experiments, we explored two different training scenarios that lead to very different behaviors of the model. In the first scenario, we mixed pixels from all fields and then split them into training and testing sets. In this setup, the model doesn't actually learn the general agronomic patterns we need. Instead, it starts memorizing characteristics of each field. As a result, the test performance looks very strong, but this accuracy is misleading because the model has already seen very similar patterns from the same fields during training. However, the scenario is still acceptable if the task allows such pixel-level mixing. In the second one, entire fields are placed either in the training or the testing set. The model can't rely on recognizing the same field anymore, so it must learn patterns that truly generalize. As expected, the performance drops, showing the real challenge of predicting yield on completely unseen fields. This is because XGBoost processes each pixel separately and has no understanding of field shape, textures, or neighboring relationship. Next, we will tell you about our deep learning approach.
Yes, so our main task was in painting missing data on yield maps caused by sensor malfunctions. And we choose attention unit, a CNN which effective on image-to-image task like segmentation and restoration. It's encoded according to structure, extracts deep features and restores spatial resolutions to produce the final yield map. We enhanced UNet with attention gates also, which allowing the model to focus on relevant regions, filter noise, and accurately reconstruct local gaps. So for the model to learn the complex relationship between fields, conditions, and yield, we engineered a 69-channel input tensor. This input integrates data from multiple sources. For example, 64 spectral channels was for 8 different spectral indexes, like NDVI, NDMI, SAVI, YEVI, captured across 8 non-overlapping temporal windows throughout the growing season. 4 DEM channels was for digital elevation model itself, along with 3 calculation terrain features, slope angle along the XY axis and the root mean square slope. And finally, the one damaged yield channel, this is the yield map itself, containing the artificially generated gaps. Our input data had a very different range. For example, vegetation indexes are small, while elevation values are large. So to fix this, we use global min-max normalization. We scaled all features to a range from 0 to 1, and this step was essential to ensure the stable and efficient model training. And after normalization, we divided our field maps into smaller patches, 64 to 64 pixels, for further processing by the model. And to specifically train the UNet to be an effective in painting model, we implemented a dynamic data augmentation strategy. For every patch, we generate random rectangular gap. We apply the validation step to ensure these gaps appear only inside the valid field area, not in the background. And finally, we hide these pixels with a -1 marker, forcing the model to learn how to reconstruct them.
We trained the model using PyTorch Lightning with the ADAM optimizer and MSE loss. Early step it monitored validation loss and model checkpoint saved the best performing weights. Training was performed with a batch size 8 for 50 epochs. We explored 3 strategies for designing the loss function. The baseline model learns only from the artificial gaps. The full field model used all valid pixels for supervision, and the hybrid approach combined both signals. We evaluated the 3 models on 2 unseen but included in normalization test fields. The full field model showed the best overall performance. However, looking at scatter plots and training loss, both full field and hybrid approaches look promising. And since the main goal is accurate restoration of missing areas, we chose hybrid strategy for further development. Further improvement of the hybrid approach, mainly through the addition of learning rate scheduler, led to enhanced results that you can see on this slide. For the missing regions, the model showed good accuracy with arrows below 0.8 tons per hectare. Values are presented in the original units here. And we also evaluated the model on an individual test field. This evaluation was performed in two different ways. First, we used the patchwise gaps test, where small local gaps were generated independently for each gap, for each patch, the same way as during training. Second, we applied a global gaps test, where larger gaps were added to the entire field before inference. Overall, model shows high stability on locals, while large missing regions are naturally more challenging to reconstruct. Next slide, please. This visualization shows how the model restores real gaps in the yield map. We used it to check how well the approach works on actual missing data patterns. And on this slide, there are the conclusions, and future work can focus on improving temporal representation, generating more realistic gap patterns, tuning hyperparameters, and expanding the dataset to increase model robustness.
And this slide is a small thank you to our mentors throughout the project. They consistently checked in, challenged our ideas, and helped us. Their support made the whole experience way more meaningful. And of course, a special thank you for the data science school itself. So thank you for your attention.
Thank you. Do we have any questions for Raul? If you want to ask, then unmute yourself, because I mute you. So no. You need to unmute yourself on your computer, because yeah.
No, is that my daughter called me, so she needed, of course, attention. Since you are talking about attention layers, yes. No, I was saying that the presentations are so interesting that I will always ask a question. So I wanted to ask you, of course, in the missing data, you can have whatever you like. You can have a black hole. You don't know, right? So what do you assume? A smoothness, or you assume that the power spectrum of the image is going to be preserved everywhere? Or basically, you say that I want to keep the same level of fluctuations everywhere in the field. What is your assumption about how to do the inpainting?
Who will be answering? Well, yeah.
Well, I'm not sure if I understood the question.
Let me just rephrase it. Imagine I have a map. I have a map with missing data, right? Okay, in the missing data, I can put whatever I want. I can put a bear. I can put a black hole. I can put whatever I like, right? So in principle, nothing stops you from recovering a bear or whatever, right? But you must make some assumptions on your in-painting algorithm regarding how you paint the holes, right? You must assume that either the power spectrum is the same and you are trying to sample from the same stochastic field, or that there is some kind of a smoothness. What are you assuming to do the in-painting? That's my question.
I think we tried to do to make model predict something similar to our known data. To like some, but not average, because average will be too easy and not exact. So
right. So you are using something like what I was saying, the power spectrum. You are saying the statistics.
I think. Sorry, I think it's some misunderstanding, because they don't take data with gaps. They take known data, create gaps artificially, train data with known part of the field, and then apply this model to unknown data. Yeah.
Right. So
this
right.
slide was just
correct. So that means that they are basically assuming that the statistics of the field are the same.
Yeah. So they basically assume that fields are fields. So nothing
exactly.
very strange can happen.
I mean, that's exactly how we do it in cosmology. I wanted to know how you do it in agriculture. In cosmology, we do the same, as you say. You take data, you just erase it, and you say, okay, I'm going just to assume that, the statistics are the same. Sorry, it took so long, the question.
Okay, yeah, I think, it's a very nice problem, actually, and I hope you will continue to work. And do you have any response from, it's for kernel, yeah?
Yes, it's for kernel.
Yeah, yeah. Do you have response from kernel about this model? Did you show them?
Yes, they were interested in it, and also it was their advice to use attention unit, and they are waiting for our pipeline also, and also they invited us to continue this project. Yes,
Okay, thank you.
I wanted
Yeah.
also to add a bit about what is NDVI because uh, the answer was not very clear. Just to clarify it. So NDVI, it's index which can show us how much near red light we can reflect from our plants, and it means how many chlorophyll we have in our plants, and how many chlorophyll means that how health are our plants.
Okay, yeah, thank you. It was question for another project, I believe, but okay, glad you clarified it. So let's go to the next presentation. Thank you for presentation. And the next presentation is Olena Litovska, Yulian Misko, and Yevgen Vinokur, mapping Ukraine's natural habitats.
Please, Elena Litovska will share the screen. Please let me know if you can see my screen.
Yeah, we can see your screen. Please start.
The presentation, yeah? Yeah. Okay. Good evening, everyone. Maybe the day for someone. Also, let me turn on my camera. Yeah, you can see me as well.
Yeah.
Okay. My name is Elena Litovska, and I will represent our Ukrainian Habitat Map project, a new approach to biotop inventory in data science environments. So let me tell you one important thing. In our modern world, our natural environment is humanity's most valuable resource, the living power of the planet that sustains and protects our existence. Without understanding what we possess, we cannot manage it. Biodiversity conservation begins first of all with accounting, and it is our responsibility as those who destroy nature the most to do everything possible to protect it and care for it before it's too late. Okay, what is a biotop actually? Think of it as a fundamental unit of nature. It's not just a list of species. It's a complete living system, the environment, the plants, animals, and all their interactions working together as one. For data science audience, we can think of it as an embedding of living world, a way to represent a complex dynamic system as a single meaningful unit. So the most effective tool for working with biotops is a map, a key instrument for managing, conserving, and restoring natural resources. But as you may see from the Korean map, biodiversity map, it was created only for European Union territory. On the west, there is a dense, well-established data set built on decades of research. And the east, Ukraine specifically, is a major blank spot, crucial lack of the on-the-ground data needed to train the models. And such a map is crucially important for post-war ecosystem restoration, biodiversity monitoring and environmental protection, integration into European Union biodiversity and habitat monitoring frameworks, informed decision-making in land use, forestry, and agriculture, like where is the best place to plant the field creation, the quality of the soil, will it affect the extinction of the vulnerable animals types, and so on.
Actually, there are so many practical applications of such a map that it's impossible to list them all. And the biggest problem is that Ukraine has no such map. The very foundation of the natural resource management for post-war restoration and for protecting our biodiversity is simply missing. We are trying to manage what we cannot see. And why didn't it exist? So there are two main reasons for that. The first one is simply walking and describing every hectare is extremely expensive, slow, and unfortunately impossible in the mined and occupied territories. And maybe we also we need people to collect those samples, but maybe we do not lack of the qualified biologist. Unfortunately, we lack of the fundings, and even now it's even more impossible because significant part of our country is under occupation. And the second reason is that modern AI needs a teacher. A standard model requires thousands, I would say even millions, if not more, of labeled ground truth points to learn from. And this is the data that Ukraine specifically now simply does not have. So what is our approach directly to the solution? It is a dynamic unsupervised mapping with satellite embeddings. As you can see from this algorithm, firstly, we take satellite embeddings, and here is like the visualization of them. This is a collection of 10-meter resolution geospatial embeddings created by Google's Alpha Earth Foundation AI model. They provide a compressed numerical representation of annual surface conditions, encoding temporal trajectories of land and coastal waters by integrating diverse data sources like optical, thermal, radar, and climate data. So this is the embeddings. Then we sample them evenly over a specific territory. Then we perform unsupervised clustering. We tried various approaches and their configurations. And the best one is, I would say, HDB scan currently achieved the most stable clustering and the best correspondence to real-world habitat boundaries. Then we matched up the cluster centroids due to specific aggregation of the embeddings. The centroids are the cluster of the clusters for the next year, for example, to maintain the consistency between the cluster which represent habitats. As I mentioned before, we do not have enough validation data, so we asked expert opinion, feedback. Luckily, we had our mentor, Oleg Prilutsky, who shared the insights with us. And lastly, we will perform a European survey, basically applying our methodology where the Korean is present. Also, I'd like to point out one important thing, that even those European maps lack of detail and not actually adaptive. For example, the latest Korean is 2018. And the UNIS map is another like biodiversity map. It's just data points which are very sparse, and also like expired data includes in them. Okay. So now we raise a very important question: can we trust the map? To answer this, we performed a validation of our test region. The results show that our model is strong at separating distinct habitats like man-made areas at 86% and the forests. It is weaker in distinguishing more ambiguous classes like grassland, which is known challenge and an area for our future work. This tells us that even without a teacher, our approach can build a remarkably accurate and reliable map. Here we have applied our clustering on the area around Kherson Dam for 6 years period. And as you may know, the dam was exploded by the Russian militaries at June 2023. And we can see how it have influenced the habitat distribution over this area. The latest one, there is no water. This is actually the after the explosion, and we see that it influenced the habitat distribution as well. Yeah, and what we can visually see is also confirmed by the math. This graph shows the Klinsky-Harabath score, a metric that measures how clear and well separated the ecological clusters are. And as you can see, the score was stable before the disaster, but it plummeted afterwards. This sharp decline captures the disappearance of clear boundaries between biotopes. In simple terms, the regional stable ecosystem have been replaced by fragmented and chaotic mosaic of new vegetation. The data clearly indicates that the landscape is now undergoing active, rapid change and has become highly fragmented. So our work is a successful proof of concept, but this is just the beginning. In the future work, we plan to implement a multi-year change tracking to monitor habitat recovery across Ukraine, develop one-by-one super resolution map for detailed local analysis. It will be on the embeddings, but super resolution mapping of the habitats. And the most importantly, we create a publicly available interactive map providing open access for ecologists, policymakers, and all citizens who care about the preserving our nature and managing it wisely. And lastly, let me introduce our team, which you can see below. There are 4 of us, and we are greatly thankful to our mentor, Oleg Porelutsky, who for providing us with biological expertise, valuable feedback to our results, and also special thanks to Josef Akman. I don't know if you're present here, but thank you for helping us and guiding us to find the way for solving complex problems on our paths and very wise advices. And lastly, here is a QR code to contact us or subscribe for updates on our projects. Thank you for your attention. We invite you to collaborate with us in preserving Ukraine's nature.
Thank you. Do you have any questions? Please.
I always have a question. So can you
Sure.
explain to, so the data are the data labeled by a human that tells you this is a pine, this is an oak, this is a willow, or this is a cement plant, or how are the data? How do you classify the data?
Yeah, I can
So-
help Elena answer.
Okay.
It's probably a bit tired from the presentation. So yeah, actually there are labeled data sets like UNIS. It's a expert-based classification system. It has like 9 classes, and it goes down below in the tree structure to expand up to 500 classes. So, but this data is very old and it's biased and like in for Ukraine territory, but we can use it to transfer the knowledge we get for these embeddings for European territory. So we can do like 2-step approach, supervised and unsupervised clustering to like fix the human bias because we have like the objective information from the satellite. So yeah, and we have also our Ukrainian data provided by Oleg Prelutsky. This is also a location like latitude, longitude, and the proper class assigned by a researcher. So it can also contain bias or be outdated, but it is what it is. And using the unsupervised classification, we are able to fix these errors in the data itself.
Can I add a little bit? So as I mentioned, the only map which is like distributed, a raster map, is a Korean, and it's the latest one is 2018. And then another one like EVA maps, UNIS maps, is just like data points somewhere on the Europe, which tells like at this year there was this habitat and with the level of uncertainty and radius. And I would say to you that the latest one, like since 2021, there are very little of them. Some are like in the last century data points, and it's, to be honest, quite hard to work with them, especially for Ukraine, especially in our
Yeah,
conditions.
and we are not even talking about the Far East or Africa or other countries where there are completely no data at all. So we can.
No, my question was more about okay, imagine I give you perfect data a perfect map, right? With I don't know, 1 meter resolution or even less, right? These are, I guess, images in different bands, right? Either optical, infrared, near ultraviolet, whatever. Okay. Now, what do you do with those pixels? I mean, they can be. I mean, you don't need to think about them as the Earth. You can think about them like Mars or whatever, right? How do you treat the data? How do you
Yeah, so,
label them?
yeah, so we have like basically two data sources. First data source is a expert labeled data. So we have the exact location and the label. And second, we have the embeddings by Google. So they used satellite data and they trained basically an autoencoder to get those embeddings. So they represent the specific location through the whole year. So that embedding has 64 bands and they are already normalized on a hypersphere and they represent the specific location. But the embedding itself does not provide us like anything at all. We have to use semi-supervised or supervised classification to make sense of it and to assign labels to it.
Okay, that was my question.
Mhm.
Thank you.
Okay, maybe we have short comment from Mentor if you have any comments, and we can proceed to the next presentation. I mean, if you can say a few words, it's fine.
Oleg, can you hear us?
Okay.
Yeah, he told me that he has electricity.
At the Zoom call.
Okay, yeah, I understand. So, are you going to proceed with this project? Maybe go to something publishable or something, I mean, interesting?
Sure, like 100% we'll continue. We have very ambitious plans.
Yeah, yeah, to open access for ecologists, policymakers, and citizens, and proceed to develop it further until it's a complete solution available for government and citizens so they can use it. And it can help track deforestation, climate change. The implications are huge.
For agriculture, planning of the field, like soil quality.
Also, we planned few publications, scientific.
And yeah, definitely not one. In the future, yeah, there are a lot of plans. Thanks to our mentors.
Yeah, I think we're gonna be developing a library for user.
So yeah, let's go to the next presentation. Thank you for presentation. And it's Anna Krishchishin and Natalia Rudenko, winter wheat yield prediction model. Who is presenting? Oh, Anna?
Unmute.
Can you hear me?
Okay, yeah. I can hear you, but very slow, very.
Sorry, 1 second. I will try to increase.
Yeah, can you go? I mean, can you talk closer to microphone or a little bit louder because we cannot hear and we cannot see your presentation. I saw such problem. It's something with you have probably Canva or something, and you have Canva raw Canva, then sometimes it's very bad. So you need to present whole screen, I think, or convert it to PDF and then.
Can you see it now? Can you see it now?
Unfortunately, no. We can see only black screen with some rectangles. So
Anna, maybe you can share.
Is it Canva? I mean, do you
No,
have Canva?
it's Google Slides. Google Slides.
Can you make reshare but share not a window but whole screen? I think that's the reason.
1 second.
Okay, maybe I will try to transfer it to PDF, but it will take time.
But yes, it's a Google slide. Maybe you can just share a link and maybe Alexei can share now.
Anna, maybe you can share, not me. I will stop sharing.
Okay, let me try.
Sorry for the delay.
It's fine.
It is only lunchtime for me, so don't worry about that.
Sorry.
Yeah. Now we can see it, and if you can make a slide or show or go to full screen, so you can see the slide better.
So the goal of our project was to develop a weekly based prediction model for winter wheat that will be operating from mid-May until mid-July when harvesting ends.
Wait a second. Wait a second. Anna, can you make a slide show? That's good. Please continue.
Yes, kernel provided us weather data, NDVI, and fertilizers input. Second slide. So we analyzed dependent variable, and it showed very strong geographical variation. So we split it into 5 clusters by k-means and included as a dummy variable. Next slide. So we analyzed weather inputs and fertilizers on a weekly basis to reflect the crop phenology and environmental stages. The strongest predictive effects were observed for NDVI and key weather parameters such as temperatures, moisture, evapotranspiration, and sunlight duration. Next slide. So we do not want to use all variables every week to exclude irrelevant or noisy. And we use 2 complementary algorithms for future selection. It's lasso to pick up variables that matter and drop the weak ones, and shape values to check which features truly influence on the XGBoost model. So Anna, you can continue. Or I can.
Okay, so each week we train a fresh XGBoost model using selected important features because the importance of weather and NDVI changes as the crop grows. We use cross-validation to choose the best model size. XGBoost builds trees in rounds, and if there is too few rounds, model is weak, and too many, model overfits and becomes unreliable. Once the model is trained, it predicts yield for every field. And it also shows which factors push the yield up or down via SHEP. This allows us to understand why a field has high or lower predicted yield. We used model quality was evaluated using standard regression metrics like RMSE, mean absolute error, coefficient of determination, and mean absolute percentage error. And what do we see is that error metrics are decreasing and the coefficient of determination is increasing, and it indicates continuous model improvement. And what are the results and conclusions of our work? The integration of XGBoost with interpretable SHEP enabled yield prediction and transparent explanation of results. The model confirmed that moisture, temperatures, and NDVI are strong predictors of wheat yield in Ukrainian conditions. And weekly retraining ensures the model adapts to evolving crop conditions and updated weather, making predictions more reliable as season progresses. Thank you.
Thank you.
Okay, thank you for being in time. And okay, do you have any questions about this result?
I'll ask my question. So can you, okay, so I like the results because here what you are saying, I mean, I like very much that you have these results, that moisture and, no, put the last slide. That's the one that, moisture, temperature, and NDVI. I want to come back to this, are the strong predictors of the yield, right? But what is NDVI? This I was told in the first presentation is how green the field is, right?
Yeah.
But is this, so is this, no, I wanted to ask you, is this like a proxy for how good the soil is? Or let me just give you an example. If I was an European farmer and I was given complete freedom and say, okay, I want to make trillions of dollars from from growing wheat, I moved to Ukraine because that's the best soil in Europe, the best by far, right? So I don't go to Norway, I don't go to Ireland, I don't go to Greece, I go to Ukraine, right? That's because the quality of the soil is so good that the wheat production is very high. So is NDVI like a kind of proxy of the soil quality, or what is it?
It's more, it's a combination, yes. It's the greenness, the measure of green, how is well-developed vegetation mass, right? And it depends on effective temperatures. If the temperatures were allowing the growth of plants, also on moisture supply, also on fertilizers, because if you input enough nitrogen or other inputs, it will also reflect. So it's combination. It's measure how healthy is the growth of the plants.
Okay, thank you. Thank you very much.
Thank you.
Okay.
Good question.
Yeah. Thank you. Okay, let's finish this. Thank you.
Thank you.
I think we have, yeah. So next presentation would be by
Right, that's us.
Lev. Yeah, you won't be the last, but unfortunately for you, Yevhen Kolomiets also managed to connect, so he will be the last. Sorry. Okay, let's please start.
Yeah. Hi, meet Mikhailo Chonka, our main stakeholder and main character of this project. He is a simple agroman that works at Zahidny Bukh. His day starts from checking his beloved beetroots. As you can see, Mikhailo is very sad. To understand why, let's go back to 2017. This is Biti, Mikhailo's best friend. Like all of us, he had a dream. He wanted to become a huge bag of sugar. However, life is cruel, so he became a small spoon of sugar, and his dream was shattered because he was not harvested in time. Mikhailo was very upset about it. He did not want the story to repeat itself. So, for 7 years straight, he was collecting data about all stages of the life of beetroots on his fields. And then he came to us for help. Beet's life begins with sowing. On this stage, the most important factors are soil, fertilization, predecessor, crop hybrid, and when it was sown. The next stage is emergence, when beetroots first reach into the sunlight. Here, it's important for all the beets to be healthy, well protected, and also we need to consider how long it took them to emerge. The last stage of the life of our beets is yield. It is time when beets' dreams either come true or get broken. Everything depends on their sugar yield. But this data is not enough. There are a lot more other factors that influence the life of our beets. Obviously, the most important one is the weather, especially the sun's radiation. which determines how much sugar the beet will have. So we extracted daily weather that included more than 20 indicators, such as precipitation, wind, snow, and so on. We mostly used monthly averages, but also tried other approaches. And using this data, we did our best to make this poor beet's dream come true.
We split our data into train, validation, and test by year because our goal is to predict next year's sugar yields, and the random split would leak future year patterns into training, giving us very high accuracy, but preventing the model from actually learning those patterns. To evaluate our model, we used a metric called SMAPE. We chose SMAPE because it gives us an intuitive percentage error that our stakeholders can easily understand, and unlike MAPE, it treats over and under predictions symmetrically. To complete these tasks, we had a lot of tools in our arsenal, from simpler options like CatBoost, XGBoost, and LightGBM, to feature selection using RapidAI, an AutoML approach using AutoGluon, and assembly models like TabM. Now let's see how each of them performed. With CatBoost, our MAPE ranged from 13 to 18%. With XGBoost, we got a better result, but here for the first time you can see a significant instability, meaning that the validation and test results are drastically different. LightGBM, once again, shows an improvement to the score, but not to the stability. This instability overall was our biggest challenge, and we cannot trust a model whose error fluctuates by 4 times year on year. We also used RapidAI with LightGBM because we had an issue with the sheer number of features that we had. We had often more columns than rows in our dataset, and we thought we needed to select them better. We tried Shapley values and we tried PCA. With RapidAI, we saw best results, and with it, we saw again an improvement to the stability, but the scores are still not low enough. At this point, we were quite sick of it. It was clear that we needed a more comprehensive solution, which came in the form of AutoGluon. This is an AutoML approach which automatically handles model selection, feature selection, hyperparameter tuning, ensembling, and feature preprocessing with minimal user input. The results were again quite a bit better, but not by much. The problem with AutoGluon turned out to be that it uses a random CV split in the training, which hampers it on the validation and test step. And the final boss of our models turned out to be TabM. This is an ensemble approach that combines multiple tabular models to improve stability and predictive accuracy. It leverages the different strengths of different models, and in the end, showed the best results.
Now let's see it in action, with Mikhailo Chonka at the wheel. Suppose we have a field with 20 beets. From the first 5 beetroots, Mikhailo got only bags of sugar. So what do you think, how long we and our model can maintain these results? Mikhailo finished with just 3 spoons of sugar and 17 full bags. Here you can see just how stable our model is across multiple years. Our aim set by Mikhailo Chonka was to achieve an error of less than 15%, and that's exactly what we did. However, Mikhailo doesn't know Python, and he won't be able to use our model directly. So we created an application for him, which enables Mikhailo to use our model in a user-friendly way. Right after solving and gathering available data, he can use our application by simply loading his Excel file into it. As a result, he gets sugar yield predictions for each field for each day in autumn. With this information, he can better prioritize which field to harvest first and which will be the last. And currently, we are working to deploy this application for Mikhailo Chonka. And during this project, we faced many challenges. Some of them we have already mentioned. The main challenge was model instability, because we don't have enough data, only 7 years. Unobserved variables such as sugar losses that occur after harvesting, machinery quality, and weather were also a problem. And as we mentioned, we had a lot of features. We have more columns in our dataset than rows. So selecting them was also a major challenge. But despite all of these challenges, we reached all of our goals. Now, every dream that beats hot in their little hearts will come true, thanks to our solution. So it's time for your questions.
Thank you. Thank you
Thank you very much.
for a very nice presentation. By the way, Mikhail Chonka is here in our meeting.
I don't think so. He at this time he generally is coming back from the field and we cannot get to him.
Okay. Yeah, I see. That's cool. So if you have any questions, then please.
So I guess my question would be, besides doing that, which is just, when he's going to get more sugar, what has he had to do to improve the yield? I mean, is there any trend in his in the validation set where you can actually tell him what he needs to do to improve much better the yield rather than wait for a prediction?
There are some. So if we look at different crop hybrids, we can tell that this crop hybrid generally produces better yields on these fields and so on. But there is no general trend if you look at total yield, because it fluctuates a lot with each year. Each year, it depends very much on a lot of factors. Like we said, there are a lot of unobserved variables. So the most important one could be that you need to have like a 2 or 3 week window with no rain to plant the seeds and to properly prepare the soil. And then you need a 2 or 3 week window to harvest these beets. And each year you either have it or you do not have it, and the window changes, and that is a very major factor. And
but that's very interesting. Thank you. That's very, very interesting result, actually. That's very, very interesting. That's what he needs to do. That's super interesting. Maybe that's why these hybrid beats are better, because they're more adjusted to actually find the windows or whatever it is. That's super interesting. Thank you.
Also, my question is about error. So you have said about 12, 10, 15% error. Yeah.
Yeah.
And what does it mean in practically? So what does this error mean actually? So you have a difference in prediction of sugar or crop amount or what?
So this is the error by how much we can miss. So we predict how much sugar we will get from 1 hectare of a field. So this error is how many more or less tons of sugar we will get from one field at a specific date. And it's very crucial to understand that for Mikhailo, it's important to understand how much sugar he will get at this specific date, so he can figure out the logistics of which field he will harvest first and which last, because you cannot harvest all the fields at once. You do not have enough machinery. You cannot access all the fields during all the season. So some fields, after like for the first half of October, they are inaccessible because of bad roads and etc. So he needs to understand which fields he can harvest first and which he can leave for later, and how that will affect the amount of sugar that he will get.
Okay, we have question.
Yes, so that's basically 13% difference plus minus in tones, and the negative value like can be ignored. So he needs one more truck to accommodate for plus 13% in kilograms or in tons. Is that the intuition?
Like yes, this is a percentage, yes, plus or minus, but generally it's not about like tracks or not tracks. The tracks are not the limitation. So you when you are start harvesting the field, you have enough machinery to take the. So your problem is not to send enough machinery to harvest the field. Your problem is to know which field to send this machinery to first, because like if you need to send one more track, you just send one more track, and it doesn't need the track does not transfer these beats all the way to the processing factory. It transfers it to a nearby depot from which another truck takes it. So it's that is not a major issue.
And the issue is then that this errors try to minimize, I guess.
So like if you harvest the beet too soon, you will not get enough sugar. If you harvest it too late, you may lose a lot of sugar. You may miss the sweet spot. So the issue is to hit this sweet spot on as many fields as you can, while taking into account your logistical like limitations and yeah, your logistical and machinery source
If I
limitation.
yes, if I may add something, then I will recommend you to distinguish first and second type of errors when you underestimate the real value and overestimate the real value, because one is very bad and another is actually good. If you underestimate the real value and he gets actually more sugar from this field, yeah, it's good. Well, maybe it's bad for model, but it's good. It's good for him. So there is a difference.
Financially it is, but logistically it's not. So for him, it's important to precisely know the amount of sugar, because like the amount of sugar changes over time, and for different fields, the graph of how they accumulate the sugar is different. So one field will first have very little sugar, then it will like rise up very rapidly, and then it will plateau. And some fields will just continue rising. And you need to know which fields will continue to rising, because you need to harvest them at the end. And the fields that plateau more, you need to harvest them first.
Okay, thank you.
And this error minimizes distance from that sweet spot.
Yeah.
Yeah, thank you. So I wish you luck and implementation of this model. It's very nice, sweet research. So let's go to the last Yevhen. He's actually he will be short because he's without presentation, a lot of time without electricity, and his laptop is dead. So now, yeah, the charge. So maybe you can just explain a bit about your research and.
Yes, thank you for attention. Hello again. My name is Eugen. We tried to do farmland analysis systems. Our data were photos, a lot of photos from drones, but we hope that we also get the data about height of this drone, about time of this photo and so on, but actually we don't have this data. So we try to find at start of our task, we have a lot of classes, like 6 or 7 classes, but after the conversation with our mentor Evgeny Kovnir, we try to like short the task and try to create models that predict one of the 3 class. There will be normal, like green vegetation, and less than normal vegetation, and big or over vegetation photos. So we try to clean the data, we try to find some way to label the data, but we cannot do this because we are not farmers. I am a chemist and I'm not a farmer, so I don't recognize in what case we have over green because this is time to crop, and in what case we have over green because it's not good for farmers, for agricultural area. So we try to use some algorithm with without labels. So we try to use clusterization, and we try to create a simple Cummins predictor that can find how many green pixels are on this photo and try to find similar photo. So we create a simple model in Python that can predict which photo are in class 1 with little green vegetation, or it will be in the normal amount of green normal vegetation, or it will be the over vegetated. It has a very big green area on the photo. After the research, we try to implement this, and we find that we have some results. I send this result to our mentor, Evgeny Kovnir. Evgeny said that is good, and he tried to find more data that we can improve our ideas, our algorithms, and so on. So I think it's short main idea, and I am glad to try to give you an answer on your questions. Sorry about electricity, but it's not about my possibility to do this.
Yeah, no, I understand, no problem.
Yeah, so maybe Alexei can give you my report, so you can see this short PDF file or document, and you can maybe better understand from that file than from my words.
Okay, so yeah, I think that that's what we can do, and we can read your report also. So now I think we can. So how I do it? Can I send everyone to waiting room? I mean, everyone who is not part of committee. Yeah.
You can create rooms, and you can just create 2 rooms and send us in one room and participants in another room. You know, like.
Okay. I actually I didn't use this creating
You make
room.
me a co-host, I can look if I can do this.
Okay, I will do this.
You see breakout rooms for like a matrix 2x2. Host tools, whiteboard, breakout rooms. You can create 2 breakout rooms. Do you follow me?
Yeah. But can
create
you
2
do this?
breakout rooms and then assign. You need them to say me whom to send where, or maybe I can let participants choose the room and then participants know where to go, right?
Okay, so you do this or me do it?
Yeah, I'm doing this.
Oh, okay.
Okay, I created two rooms. One is named orgs and another one is called summer school participants. I will open them and you need just to choose your room. So please choose the proper room and go there and then we will reconvene. Do you see now an opportunity to choose a room?
Yeah.
Yes.
Yeah.
Oh.
It came to my mind that probably we should stop recording before our process of
I don't know what to do. I can't. I can delete.
I can cut this part in video later, so it's no problem. Mm-hmm. Okay, I hope everyone is here and we can announce the results and everything. So it was very close run, and many projects. The projects were very good, and it was tough call to decide who would be the winner. So third place is Mapping Ukraine's Natural Habitat by Elena Litovskaya and Misko Evgen Vinokur. Cool. Second place is Sugar Beets Reprognosis, Lev Pepivida, Katerina Shvahulyak, Elena Hnip. So congratulations. And first place, Yegor Yanvaryov, for very nice work and very nice images and everything. So yeah, congratulations. Yeah, but I can say that all projects were very good. This year it was something new. We never tried this before. I mean, in some specialized scale, and I hope you will continue and you will create something nice. And see you next summer school. And Yulia, can you make some closing remarks for this?
Yeah, first I wanted to say thank you all, for joining summer school from the very beginning, attending it, active participation, as well as your, will to continue and to do more and to do these projects and to work together and to work maybe outside your comfort zone, with data sets which are coming from business. And this is like a very special customer here. And some of you even take additional steps, to come closer to this customer and to see how this can be useful for them. So this is a very interesting experiment also for us, because having this school supported, I think, the third time already from the National Academies of Sciences from US and Simon's Foundation. We are trying to see what is the best angle we can look into this interface. And we are thinking, yes, data science itself is like a cool place, and this is great expertise, and it is great to see young people, joining and working on this. But also we were thinking to extend a little bit and to see if these interfaces can be built between scientists and business and in very specific niches. And I think seeing your projects today is definitely a measure of success for us and success of this model and this idea. We definitely will look into this, as a maybe next iteration of this program, to have more of this kind of specific interactions between actors from different fields. And thank you for inspiring us, to do more. I want to say thank you for each of you. I want to say thank you for UKU team putting all this together and facilitating this all interactions. They not only organized the event itself, they also worked very hard, to ensure there will be good partners for you, both academically and in Ukrainian agribusiness. So I really appreciate this, and I'm grateful for what you're doing. And I really hope that these projects for you won't be finished today, and your dreams and your ideas and your thoughts, you will find the way, to proceed with this and to build stronger partnerships for your future, but also for the topics you've been discussed. I think this is very crucial, not only for you as researchers or professionals, not only for business, but for Ukraine as a country, as economy, for our future. So thank you very much. Let's make us, inform us about your next steps. We would love to learn about how this progressed and see if there can be anything we can do in future. Thank you.
Thank you.
Yeah. I wanted to thank you also for creating this competition summer school. We gave us the opportunity to have my team members, to have this friendship, to have this project, to continue this project, to have those mentors. Actually, this is a great opportunity. Thank you so much.
Thank you. Thank you. Have a nice evening then. And I will probably send you some follow-up form to fill in so we can get responses and everything, but it would be probably next week. So yeah, bye.
Thank you.
Yeah, feedback is very important. So please fill in that form because we want to learn from you and do something better next year. So thanks.
Thank you.
Thank you very much. Thank you.
Thank you. Goodbye.